Welcome to our channel Science Scope. In my last video, I talked about different types of space missions based on their orbit around a planet. In this video, we will talk about another type of mission based on its trajectory. There are 4 categories of trajectories that spacecraft can take to reach their destination. We already talked about one of them in my previous video, the orbital insertion, where the spacecraft is placed into an orbit around the planet. Then there is the return mission, where the spacecraft returns to Earth after visiting the planet. These 2 mission types were discussed in detail in the last video. So let us move on to the other 2. One category is the flyby. A flyby is a trajectory that does not involve placing the spacecraft into orbit around any body in the solar system. It is what it sounds like. The spacecraft flies by the planet or planets on its way to somewhere else. Of course, strictly speaking, all trajectories are really just flies by, because in the heliocentric reference frame, the planets themselves are flying by each other. But in this video, I will refer to the common use of the term fly. So this class includes spacecraft that perform reconnaissance of our solar system. They follow a continuous solar orbit or escape trajectory, and are never captured into a planetary orbit. To do their science, they must have the capability of using their instruments to observe targets as they pass. Ideally, their optical instruments can pan to compensate for the target's apparent motion in the instrument's field of view. So basically, these spacecraft need to be capable of making a single, very detailed flyby, then continue on to the next target. Flybys require careful planning to make sure the spacecraft comes within the required distance of the target to perform its science. For example, if the camera has a resolution of 1 kilometer per pixel at a distance of 1,000 kilometers from the target, then the spacecraft needs to come within 1,000 kilometers of the target to get a good look at it. But it also cannot come too close, as this could damage the spacecraft by getting hit by debris or radiation. Another key consideration for flybys is that these spacecraft must downlink data to Earth. There are some examples where the flyby spacecraft transmitted data while in the vicinity of the target, but most of them store data on board during the periods when their antennas are off Earthpoint. This means that when the spacecraft reaches the target, it has to start transmitting huge amounts of data to Earth. This creates a demanding communications period right after the flyby. Furthermore, flyby spacecraft must be able to survive long periods of interplanetary cruise. Depending on the destinations, the spacecraft may have to travel for years without performing any major maneuvers or making any significant course corrections. And during this time, the spacecraft needs to maintain health and be ready to perform at the times of the close encounter with the planet. Flyby spacecraft may be designed to be stabilized in 3 axes using thrusters or reaction wheels, or they may spin continuously for stabilization. Some examples of flybys are the Galileo orbiter, which flew by Venus, Earth, and Mars before arriving at Jupiter. Also, the Cassini orbiter flew by Earth, Venus, Mars, and Jupiter before arriving at Saturn. You might think that these are not flybys because the spacecraft did end up orbiting the planets. But remember that we are talking about the trajectory to the planet, so the fact that they later went into orbit around Saturn doesn't matter. Our prime example of the flyby spacecraft category is the pair of Voyager spacecraft. In fact, Voyager 1 and 2 are the only spacecraft ever to fly by more than one planet. The Voyagers flew by Jupiter and Saturn and continued on to explore the outer solar system. After being launched in the late 1970s, the twin Voyager spacecraft used gravity assists around Jupiter to help swing them on their way to Saturn, and they returned stunning images of the 2 planets as well as their moons. After completing their primary missions, both Voyager spacecraft left the heliopause behind in 2012 and entered interstellar space. Both continue to send back data to Earth more than 45 years after launch. Another interesting flyby mission was the Stardust cometary sample return, which flew by the Earth in 1998, and then the Wild 2 comet in 2004. During the flyby, the spacecraft performed a series of maneuvers to point its dust sampling collector towards the comet. At closest approach, the spacecraft was traveling at 15 kilometers per second relative to the comet and passed within 238 kilometers of the nucleus. After leaving the comet, the spacecraft headed back to Earth carrying with it samples of the comet dust. The spacecraft successfully returned the dust samples to Earth in 2006, providing scientists with the first opportunity to study pristine cometara material. There are many more examples of flyby spacecraft that visited only one planet or moon. Here are a few. Mariner 2 was the first successful interplanetary probe to fly by Venus in 1962. Mariner 4 flew by Mars in 1965 and sent back the first close-up pictures of the red planet. Mariner 5 flew by Venus in 1967. Mariner 6 and Mariner 7 flew by Mars in 1969, sending back the first close-up views of the Martian surface and helping to map the planet's surface features and seasonal color changes. Mariner 10 was the first spacecraft to fly by Mercury in 1974. Pioneer 10 was the first spacecraft to fly by Jupiter in 1973 and the first to cross the asteroid belt. Pioneer 11 followed in 1974 and became the first spacecraft to fly by Saturn. It also performed the first planetary spacecraft mid-course maneuver to alter its trajectory to pass near Saturn's largest moon, Titan. And finally, New Horizons flew by Pluto and its moons in 2015, returning the first close-up images of the dwarf planet and its moons. That was the first probe ever to visit Pluto. There are many more examples of flyby spacecraft, but I think you get the idea. These are missions that fly by one or more planets on their way to somewhere else. They are used for reconnaissance or to deliver probes to other parts of the solar system. The main advantage of the flyby approach is that it is relatively inexpensive compared to the other methods. By taking advantage of gravitational assist maneuvers, flyby missions can reach very distant destinations without having to carry heavy propulsion systems. The main disadvantage of flybys is that once the spacecraft passes the target, there is no opportunity to return and revisit it. Now let's see how this compares to the fourth and final method, the return mission. Return missions are similar to orbital missions in that the spacecraft is placed into an orbit around the planet. However, unlike orbital missions, the spacecraft eventually leaves the planet and returns to Earth. Return missions are typically used to return samples from the planet back to Earth for analysis. Of course, not all planets are suitable for sample return missions. The main reason is that they need to be relatively close to Earth. The further away a planet is, the more propellant is required to launch the spacecraft back from that planet. In addition, the communication distances become very large and the amount of data that can be sent back decreases. For example, a signal sent from Voyager 1 at its current location would take more than 13 hours to reach Earth, and a reply to that signal would take more than 14 hours to arrive back at Voyager 1. So trying to communicate with a spacecraft at Neptune, Uranus would be extremely slow and difficult. This is why the return missions are limited to the inner solar system. The first return mission was the Apollo program, which returned astronauts from the moon to Earth. Other examples of return missions include the sample return missions to the Moon, Mars, Venus, and the asteroid Gaspra. These missions use a combination of orbital and return trajectories to bring the samples back to Earth. These missions are typically very complex and expensive, but they provide an unparalleled opportunity to study samples from other worlds. The main advantage of the return mission is that it brings samples back to Earth for analysis. This is the ultimate goal of many planetary exploration programs. The main disadvantage of return missions is that they are very expensive. In summary, we have four main categories of missions based on their trajectories. These are the orbital insertion, the return, the flyby, and the orbiter. Each of these mission types has its own advantages and disadvantages. The choice of mission type depends on the specific goals of the mission. If the goal is to simply explore a planet or its system, then a flyby or orbiter mission may be appropriate. If the goal is to return samples from the planet to Earth for analysis, then a return mission is necessary. Hopefully, this video helped you understand the different types of trajectories that spacecraft can take to explore our solar system. Thanks for watching, and see you next time. What we've been doing for about 5 decades now is flying spacecraft out to planets and other objects in our solar system. But there are 2 different ways that we do this, either by putting a spacecraft into orbit around a planet or by sending one on a flyby trajectory. And while orbital spacecraft are fascinating in their own right,